Okay, hope you guys had a good weekend. So we're gonna get back to our discussion of language models, and today we're gonna talk a lot about attention and transformers. So last time we were discussing what does it take to do a really good job to predict the next character in this sequence. And with our knowledge of English, we figured out it's probably going to be yes, because run is a verb and dog is singular, and we know that when you conjugate run, it should be runs if the subject is singular. And so at a high level, what we realize in doing that is that we really have to understand this sentence, or whatever string of tokens it is, at a high level. We need to understand the role of every single one of them in the sequence, as well as the connections, between all those tokens or those embeddings. And so the ones that are most important for prediction are not necessarily just the most recent ones, but really a lot of them. And so basically, and you can imagine that if you want to scale this up and do more and more powerful things, you'll need longer and longer sequences to work on. And the trouble with these previous generation models like RNNs, LSTMs, GRUs, is that they are based on having an internal memory, and they struggle to really understand the sentence as a whole, especially when it gets very long. So basically this 2017, the transformer came out, which is based on the attention mechanism. And the attention mechanism tries to sort of address these issues. And what it does is it uses a number that describes the strength of every one of these tokens' impacts on predicting this one. And so today we'll learn about how those numbers are computed and all that stuff. Okay, so that's kind of the idea, high-level idea behind attention. And then the high-level idea about how transformers work is that they receive this sequence of embeddings, like they receive this sequence, and then they process this entire sequence over several iterations. And at every iteration, they try to make more sense of all the different embeddings within the original sequence. Because when it starts, all those embeddings are set using the codebook, which only knows about each token in isolation. So we talked about how the letter E in English can be used in very distinct ways. And so the token for E really needs to kind of capture all those ways simultaneously. But as we learn more about this sentence, we can learn how is this particular E used, and then what is the meaning of that particular E. And so we can do that over several iterations with the transformer. So the first time it just starts out with knowledge of each one of these embeddings just on its own in isolation. And then as a first pass, it tries to get a better sense of what all these things mean. And then as a second pass, it tries to get an even better sense, and so on, because it can't do everything immediately in one step. So that's how it works. So there's going to be a total of L stages where the entire sequence is processed. We will always refer to X as the input and Y as the output. Here, I'm just denoting the stage in a superscript, L, little l. And as you go from one stage, you take in X and you output Y. Then for the next stage, you copy these Ys, or those Ys are the input for the next stage. And we call the embeddings at the intermediate stages contextualized embeddings, whereas the ones at the very input would be token embeddings. And then once we're done with all our processing, we then have a sequence of embeddings. But those new contextualized embeddings, you're not going to find them in the code book exactly. So you need to bring them back to sort of that world of the code book, and you can do that in 2 steps. So first, you unembed them using multiplication by a matrix. And that matrix is dimension n by d, and if you remember, d is the dimension of the embedding, n is the number of words in our vocabulary. So this matrix brings it back to something of the same size of our codebook. And it also, the strengths of these will reflect how close each y is to all the entries in the codebook. So for example, we talked about how there's many different meanings of E. So as you go through the transformer stages, you will eventually learn perhaps the correct usage of E in this sentence. And then when you multiply it by U, you will find that the original token for E still captures that embedding, and so that will give you a large positive output in this vector. Whereas maybe there's another E in the sentence that was used in a different way. Well, this unembedding matrix also knows that that's another way to use E, and so when you look at the logits of the vector again, that other usage of E will also show up as being associated with the original token E. So basically, this is just a way to go from the embedding space back to the vocabulary space. These are real numbers, logits, positive and negative. And then we want to convert them to a PMF, and we do that with the softmax. The temperature is something we can control. The larger the temperature is, let's say the smaller the temperature is, when you divide by it, these numbers get large. And the way the softmax works is that it can get very peaked. So that means you have a lot of probability concentrated only in a few places, which means not a lot of randomness. So you can use this temperature parameter to control how much randomness you want during generation. So this is sort of the high level intuition behind how the transformer processes things. And today we'll get into the details of exactly how it does the processing. All right. Are there any questions so far? Okay, so let's talk a little bit about how you train it to do autoregressive text generation. So each one of these is one of those processing stages, and you start with your input sequence. Let's say the overall goal is to predict the next letter, which is probably going to be O. It could be a space as well. And so what you do is as we talked about, you convert these tokens to embeddings of length D. We will talk about positional embeddings in a moment. And then they go through the transformer block. So at every new stage, they get refined. And when you're done, you have the sequence of Y embeddings. Then with this unembedding process, you map them to dimension n, number of characters in your vocabulary, n. And then if you wanted to generate, you can then generate the next character by looking at that PMF. The way it's trained, though, is we have this long training sequence, and in that sequence, these were the first 4 characters, and this is a shift of the sequence showing that the next character is the letter O. So we train it with many batches of data like this. This is just going to be one element of a mini batch. And when we train it, we don't only try to predict the next character. When you train a transformer, you actually try to predict all these different characters given this one. So, and we'll talk later today about there's sort of a way to prevent trivial copying of this to this and this to this and so on. So essentially what will happen is you will use H alone to predict E, then you'll use H and E to predict L, you use HEL to predict L, and you will use HELL to predict O. So you will have a different cross-entropy loss for each one of these targets, and you add them all together to get the total cross-entropy loss. So that describes how the training is done. Any questions on that? Is that making sense? Okay. And then when you actually do autoregressive text generation, you take some input sequence, you make a prediction from that input sequence. So you start with these PMFs, and then to get actual characters, of course, you need to draw samples from those PMFs. But for generation, you actually don't worry about these. You only use this next one. So you just sample from this PMF here, and maybe you sample an O, maybe you sample something else, but that is the one that you will append to your initial sequence. So you start with this HELL. Maybe this is your prediction. You can see the prediction got this wrong, but you're going to throw that out. You're not going to use that for generation. You're just going to take this and append that onto these. So your next input sequence will be this, and then you'll predict forward again and just repeat the process. Every time you'll generate one new character. So that's how we do the generation. It's the autoregressive part. Okay, is that making sense? Okay, great. All right, so we have focused on this autoregressive generation, or you could say next character prediction, but this is just one of many ways you can use a transformer. For example, another thing you could do with a transformer is you could build a classifier. So I'll show you later today some details, but so what you could do is you would get this output sequence, and then you have, you might just average all these output tokens down to one D-length vector, and then you build another linear classifier that uses those as features to predict whatever your label is. So for example, maybe you have a sentence, and you're trying to determine, is this a positive or a negative? Maybe it's a movie review, and you want to have a classifier that says this is a positive review, negative review, or something like that. So that's called sentiment analysis. But of course, as we know, there's many, many other things you can do with classification. Another application of transformers would be machine translation, translating from one language to another. And we'll talk about that later, probably later today as well. And so when you do that, you actually use a pair of transformers. One transformer extracts the meaning of the input language, or the text in one language. It extracts the meaning and it stores them in like a hidden state vector or a latent vector. And then you have another transformer that sort of does this autoregressive text generation, but it's informed by the content from that latent vector. And then another application is maybe you're not working with language at all. Maybe you just have a multivariate time series. So you just have a sequence of vectors evolving through time, stock market data or whatever it is, and you want to predict forward in time, one step. You can use transformers for that too. It doesn't need to be about language. You can use attention for that too. So as we go forward, we'll see examples of these, and we'll just think of transformers as general sequence-to-sequence processors rather than focusing only on next character prediction. Okay. All right, so we're going to learn about self-attention now, and we're going to kind of start with the simplest possible variant of it, and then we'll make it a little bit more complicated. So as we discussed before, we would like to know how each embedding or token in our sequence is predictive for other ones. And you could basically say this is like the strength of the relationships among the different elements in your vector valued input sequence. So this is the input we're working with. Each one of these is a vector. There's a total of T of them. People refer to this sequence as the context. And they refer to the length of that sequence, T, as the context length. Okay, so in its very simplest form, to process the input to produce the output, this is what you would do. You would, let's say we're creating the ith element in this sequence. So what you're going to do is you're first going to compute these raw weights just as inner products. So if we're computing yi, we're going to do inner products with xi, and with all the other xj. We're going to call those weights w prime ij. Then these weights can be positive, negative, they're not normalized. We're going to normalize them by putting them through a softmax individually for each I across j. So now we're going to get a sequence which you could think of it as a PMF, but we're not going to use it as a PMF. It's really just a normalized version of these raw weights. Once we have the normalized weights, we simply use those to weight all the different inputs of x to create a given yi. Okay, so basically, we first use inner products to compute the raw weights, then we normalize the raw weights for each I, and then we just use those normalized weights to linearly combine the inputs to give each output. So is that sort of making sense? Okay, so why do you think, why are we using this inner product here? What's the intuition? What does an inner product tell us between two vectors? Yeah, how close together they are in terms of are they pointing in the same direction? If they're orthogonal, the inner product's 0, right? That means in some sense they have nothing to do with each other. The more they have to do with each other, the larger the inner product gets. Of course, the inner product is also going to be proportional to the norm of xi as well as the norm of xj, so it's not purely about direction. But functionally, this is telling us how close are xi and xj, how related are they to each other. So if we're talking about language, these would be different embeddings of some token. So how related is E, the letter E and the letter A maybe, and maybe because they're both vowels, you would find that they're more related than letter E and letter X or capital X or something. And then the way that the weights are used is when creating yi, you're going to weight each of the xi's by how related to yi it is, right? So the more related these are, xi and xj, the more you will use xj when forming yi. Okay. All right. So again, this can be done with any kind of time series data. It doesn't need to be language. All right. So a couple important notes is that when doing this, the input sequence order is unimportant in the sense that if you permute the input sequence xi through xt, or x1 through xt, the only effect will be that you permute the output sequence. So there's basically this permutation equivariant, it's called. It doesn't really know, what is the beginning, what is the end. It just is this very generic weighting function. The other important thing is that there's no learnable parameters so far in what we've described. Now, it could be that the xi's could be, coming from a learned encoding, yes, but in here, there's nothing learned. So we haven't put that in yet. We're about to put that in. All right, so this is self-attention in simple form. Let's look at a picture of this. So when we're making this yi, which happens to be I equals 2, you can see how these are the different inputs, the input embeddings. These are, this would be three-dimensional embeddings, context length of 4, and these are the weights that we're using to multiply each embedding and then summing them to get y2. The way that we have computed this weight here, this is the weight when creating y2 and using y or x1, we got this from the inner product between x2 and x1. This weight we got from the inner product between x2 and x2 and so on. So just a visualization of what we saw on the previous page. Okay. So when looking at this, you realize that the different x's are used in basically 3 completely different ways when in this processing, in attention. So one way in which they're used is that they are used in some kind of weighted linear combination. Okay, so the version of x that's used for that purpose you think of as the values. Now to compute the weights, notice that if we're making y2, that you'll see x2 is present in all these places. Okay, so, or as if we were making y3, you would see x3 in all these places. So there, that's called the query. It's kind of like saying, when making y2, you're looking for something. And you're looking, is that something present in my x values? This is what you're looking for when making y2. And then finally, we have these. And the indices on these x's match the indices on these x's. And this is the other part. When you're looking for something, this tells you how much of that something is actually in input sequence 1. So it's what you're looking for, what you're trying to match. This is how much, or where you're looking for that match. And then if there is a strong match, if that weight is large, this is how much you contribute or communicate to the output. So those are the queries, keys, and values. Okay, any questions? All right. So that's exactly what I was describing here, but with equations. So here we have the value that you use to create yi, and then in forming these raw weights, you have the query. That's the one whose index matches the output, and then the key is the one whose index matches the value. Okay, so x is used in 3 different ways. Query, what yi is looking to match. Key, what xj contains for the purpose of matching. And the value is what xj will communicate or contribute. So because x is used in 3 different ways, it makes sense to apply 3 different transforms, learnable transforms, so that it can function it can learn to function in a productive manner. So basically, this value, you will replace, instead of using x, the raw x there, you will use this vj, which is the transformed x. And this is a square transformation, so it just takes you from d-dimensional vector to d-dimensional vector, and it's something you can learn. Similarly, over here, for the key, you're going to use not the raw xj, but you're going to use this transform version, which we'll call kj. And then over here for the query, instead of the raw xi, you're going to use the transformed xi, which is qi. Okay. And then there's one more kind of minor detail, but it helps a lot in the implementation, is because these raw weights are going into this softmax, and we know that softmax has basically when you have like one logit is much larger than the others, things get really concentrated in the softmax. So to prevent that from happening, or to kind of scale it to the size of the input, you divide by the square root of the input length, and that helps to keep the values in a good range for the softmax so they don't get too large and too amplified. And this, when you do this, this is now called scaled dot product attention. So the learnable parameters for us now would be these 3 matrices. And we would learn them, depending on our overall objective. If we're doing next character prediction, then we described how we take in the sequence, we try to predict this, we have cross entropy loss for each one of those, we sum those together. So we would be basically learning the matrices so that we do an overall good job at that task. Okay. All right. So this is basically the essence of the transformer layer. It's pretty important. Is this making sense? More or less? Okay. All right, so this is kind of the simplest version of what you might implement in practice. But it turns out that it's not maybe flexible enough. If you look at how the raw weights are computed, right now, we have, this would be our key, kj, this is our query, qi. And then this is just writing them, more explicitly with the matrix transformations. And you notice that, for every ij pair, you will always have this way of computing it, which means there's sort of only one way in which attention is being computed. So you might think, well, it's maybe not that simple, because even if we're doing character prediction, maybe we want to, have some way of, like, one version of attention that is saying how vowels relate to consonants, and maybe another one says how consonants relate to vowels, and another one says how punctuation relates. And so this is just sort of like one flavor of how an xi and an xj can combine. So you might say, well, okay, one thing you could do then is you could just have like a whole bunch of copies of these matrices. So maybe you have like 10 versions of each of these matrices. Well, that would work. Now it's going to scale up your computation by a factor of 10. So that's not very efficient. So what is done usually is it's kind of like a compromise. So you take each of these matrices. Each of these matrices here, we'll just abbreviate them as W star. Star could be Q, K, or V. And you split that matrix, kind of like this, horizontally into H submatrices. H is some integer number like 4 in this picture. And the size of each submatrix is now going to be D over H. And then what you'll do is separately perform self-attention for each one of these R's. These are called heads. And so as a result, through the self-attention mechanism, let's see, so separately perform self-attention for each R, you will then get H different output sequences yi. And R here is not the power, it's just denoting which. This is like R equals 1, 2, 3, 4, which of those you're working on. Now these yi's, because we have reduced the dimensionality of these heads, they are all 1/4 of our full embedding size. So here we're stacking them back together to get back to the full embedding size. And then there's going to be one more learnable matrix that can combine these different versions of attention to get the final output yi. Okay, so in doing this, by this splitting, we haven't introduced any additional complexity. It's identical number of multiplications and additions and stuff. There is one, this is new, so this is a little bit more complex, but it's worth doing this one last transformation. So overall, it's just a small increase in complexity due to one more matrix multiply. And this is called multi-head self-attention, which is what's used pretty much always in practice. Okay, so this is just a picture showing that this is like the transform for WK. This is split 4 ways. And then when you do attention, your input, your X, maybe this is like your XJ, is the full size D. So you do this inner product along this dimension, and this is the different, this is like this matrix, this vector is now going to be 1/4 of the size that it usually is. This is 1/4 of the size it usually is. Okay. All right, so that's multi-head self-attention. Any questions on this? Making sense? All right. So this is a picture that tries to show everything together. So we start with an input sequence. So this is the dimension D. This is the context length T. So we have 5 vectors in our time series, or in this little snapshot of the time series. And we first compute using these. We do these, you can think of it as like doing a big transformation that's square, but then chopping it up. After you do the transformation, you chop it into H heads, which in this picture is 4. So this would be for head 1, head 2, head 3, head 4. This is standard attention, but all the embeddings are now a quarter of the size of the original ones. And then once you're done, you stack your outputs. Now you have something of the original size and length, and then one last transformation to get you to the final output for this layer. Okay, is it making sense? All right. Okay, so when you look at papers, you'll see that often things are described with matrices. So what you do is you stack the different embeddings in your time sequence as rows. So here we're going to have matrices that have T rows and D columns, which is pretty much the way we've done things all semester. You always have different samples coming down the rows, different features going across the columns. And once you have matricized your X's, your inputs, and your outputs Y, then you can describe the queries, the keys and values as matrix operations. And people write softmax this way. They do this matrix multiply, and then you apply the softmax over the rows of this matrix. And then this is the output, This is computing the weights. These are the values. This is plain self-attention, so no heads. And if you have multiple heads, what you can do is you can express this extraction using a matrix that has like an identity here and zeros here. So this would extract the first, let's say, quarter of the elements. So you have your full square matrix, you pass it through this wide matrix, and this will extract the first quarter, or you build this a different way and it extracts the second quarter and so on. And then your expression gets a little bit more complicated. But you can see it's the original attention above is done, and then you stack things together, and then you transform the output. And that's your multi-head attention. Okay, so just showing you these because this is what you'll often see in papers. Okay, so any questions on attention? Okay, so now we know about attention. So what are transformers? So basically, generically, a transformer is some sort of deep network constructed using stacks of usually identical blocks, and those blocks include attention layers. Now, there's different ways that they can manifest, but the one we have here pictured below is a very common version of this. So this is just one transformer block, so one stage of transformer processing. You would maybe cascade a number of these, but let's look inside the block. So here is the self-attention thing that we just described on the previous couple pages. But the way that it is implemented, you notice, there is what's called a skip connection. So if I set all the weights in my attention network to 0, and it outputs 0, you would, in that case, the input would just be passed directly. So it's not like 0 weights would kill everything. They would just not change the embeddings. Okay, so what that means is that these green blocks, like the self-attention block, is just causing an additive perturbation or a refinement of the embedding. Okay, so here we go through self-attention, but with a skip. And then there's something called layer norm. Layer norm is a lot like batch norm, except rather than taking averages across your batch dimension, you take averages across the feature dimension, which in this case would be D if we have D embeddings, D-dimensional embeddings. So very similar to batch norm, its purpose it has, so this is where you're subtracting the mean, dividing by the standard deviation, and then you're scaling and shifting by some learned parameters to get your outputs. There's actually kind of a typo in here. I'll upload a corrected version. But basically it works a lot like batch norm, just on features rather than batches. Okay, that's the first half. Any questions there? Okay. Second half is we have these multi-layer MLPs. You know, our neural network, multi-layer perceptrons. And these are usually pretty simple. They're just usually a 2-layer, so just one hidden layer. And the hidden layer, originally, they were based on ReLU. More recently, they use GELU, usually. And they process each item in your input sequence separately. So this guy, you know, after it goes through self-attention, passes through an MLP. This one passes through an MLP, and so on. And then there's another layer norm at the output of the MLPs. And then this is one transformer block. So this is what happens to get one refinement of your X sequence to get your Y sequence. Is attention followed by MLPs. The MLPs also have a skip layer. So maybe they do nothing. If they do something, it's just like a refinement of what came in. Okay. So like typically you stack those blocks together. Maybe you have like, I don't know, 4 or 8 of them, not like hundreds of them, just a few. Okay, so that's basically how transformers are constructed, and this is one example. Still very close to how they're done with language models. We'll see another variation, but okay. So what if we want to do classification with a transformer? So let's say we have a k-array classification task. So maybe we get a string of text and we want to say, is this positive, negative, or neutral? So in that case, we would have k equals 3 classes. And so you could put it through the sequence of transformer blocks to refine the embeddings. And then you can average across time to reduce this down to one vector of dimension d. And then you just put it through a linear classifier. So you have a linear matrix plus bias, linear weights plus bias. And now you get logits. So these are real numbers. And from the logits, you could convert them to a PMF if you want to look at them as probabilities. Or you could just choose the index of the largest logit if you want to just make a hard prediction. Okay, so basically, this part is the same. What has changed for classification is just how you process the outputs of what the transformer gives you, averaging, and then you would use cross-entropy loss according to your classification task, not next character prediction. Okay. All right. Any questions with that? So that's like just another way you can use transformer. But there is an important issue here, is that remember how we said that the attention layers were permutation equivariant? So what that would mean is that if you put in a sequence, dog bit man, that you would get some output sequence, a refined version of dog bit man. But then what we're saying is you just average them, right? So what if instead I put in man bit dog? Well, now I would get man bit dog, but I average them. So I would get the exact same thing. So the classifier is not going to be able to determine the difference between dog bit man or man bit dog, which, as we know, are very different things. So that shows you that you need to add one more thing in the transformer usually, which is position embedding. Position or position information. There's a couple ways to do this, but basically you add something that tells you that this is the first word, that this is the second, third, and fourth. so that the transformer blocks can interpret the location in the sentence in a meaningful way. So there's basically two ways to do this. There's position embeddings and position encoding. In position embeddings, you just treat, okay, so basically you're just going to add a vector, ti, to each xi, and in position embeddings, you just treat them as learned parameters. So here is like our x1, this is our t1, this is our x2, t2, right? So these are, you just treat these as learnable parameters and you learn them to minimize your cross-entropy loss. Another thing that is common to do is to not learn them but design them. Just make them something reasonable. And typically that's done with this sinusoidal encoding where you use like a sine wave for the even samples and a cosine for the odd samples. And this is just kind of a picture using a heat map. Here you have, this is position I, and then this is the embedding dimension D. So this would be for 64-dimensional embeddings, and looks like a context length of 1,000. So you can see how the pattern across D changes with time. So you have some parts of this that are changing very slowly. So, you know, in 1,000, over 1,000 times, they only changed, you know, portion of a cycle. And then down here, you have very quick changes. So like just from one to the next, you get oscillations. So these parts are not even really being used for this context length, but if you made the context length longer, then you would start using these to also encode dimension. You'd see these kind of things, these shapes kind of go up like that. Okay, so this is designed, not learned, or you can just learn them. So that's how we tell the transformer where the different tokens are in the sequence. So this is used here. We also saw it with the next character predictor, although I didn't call attention to it then. Okay. So is position information kind of making sense? All right. Okay, so this, we've kind of seen a version of this before, but now we can maybe understand it better. So we have, this is going to be for autoregressive text generation again. We have our input sequence. We encode those to embeddings with our codebook, which are understanding these characters in isolation. But then we also add our positional embedding now to tell us where we are within the sequence. Put it through these transformer blocks, which are usually identical in structure, although each one will have its own learnable weights. And we get an output sequence. And for this application, we train so that we get basically like a shift of the sequence. But as we said before, if we're not careful, the learn blocks could learn to do something very simple, which is just to sort of store this character and apply it here. Store this one and apply it here. In which case, we wouldn't really be learning anything about language, right? We would just be shifting. The transformer is just learning to shift, basically cheat. So in order to prevent that from happening, we need to use something called causal masking. And the causal masking is what essentially you place some constraints on what happens here so that when predicting E, you can only use H. When predicting L, you can only use these two and so on. Okay, so how does causal masking work? Basically what you do is you do a matrix, not a regular matrix multiplication, but like an element-wise multiplication. That's what this means, Hadamard product. So you have a square matrix. This is also a square matrix. You do an element-wise multiply. There's actually another typo here. These should all be zeros. Okay. And so they call this the mask matrix, but actually it's really a log mask matrix. So if you take the log of 0, as you know, log of 0, or sorry, if you take the exponential of 0 gives you 1. An exponential of minus infinity gives you 0. Right, E0 is 1. E minus infinity is 0. And so because this is inside the softmax, it is going to be exponentiated by the softmax. So essentially, if you think about the softmax is applied row by row. So what that means is for the first row, you're taking whatever that row vector is, and you're doing a pointwise multiply by this, which is essentially, no, actually, sorry, these, I made a mistake. These guys should be ones because we're doing a multiplication. So this is going to be keeping the first element of this row vector, but you're going to be forcing all the other ones to minus infinity. And so when you do the softmax, it is essentially going to, the weights it's going to give you are going to be 0 for all these, and then the original weight for that. Now for the next row, the second row, you're going to multiply it by this. So that's going to force the attention values for all of those guys to be 0 and keep whatever contributions you have for here. Okay, so that's how it works. And essentially what that means is that if you are predicting this first output, it does not allow you to take any contributions from the future ones. So as we know, when we do it with a shift, this is like HEL, L, this is like ELL. So this would be cheating, but we don't allow this to happen through the mask. We don't allow any future things to be used to predict this. So for the next one, we allow the first two, but we don't allow any future ones, and so on. Okay. So there's another way that maybe we could have done this. Maybe we could have applied this is the most reasonable way to do it. Okay, is that making sense, how this masking is? Okay, so this is called masked attention, and this is what's used whenever you want to do forward prediction, but in other applications where you're not doing forward prediction, you don't necessarily need to use this mask. Okay, so that basically, we've gone through the transformer. We now know enough to code everything. It's coded in the demo. There's different ways to code it in PyTorch. In fact, there's a function that does all of this for you in basically one line. That's the quickest way. But I also coded it in a way where you go inside the transform blocks, and then you can see, you can code this with a certain attention block. You can code this with a layer norm block. You can make little MLPs manually and so on. So you can see that version of it as well. But when you're all done, let's see how well this works. So we have our tiny Shakespeare data set. Because I was just using my old MacBook, which is pretty weak, I couldn't make the model very powerful. So what I used is context length of 64 characters. I used 64 dimensional embeddings, 4 heads, 4 layers of transform processing. I used positional embedding, so that's the learned version, causal masking, which we need, and dropout, which we've talked about in the context of MLPs as a way of making things a bit more robust. And otherwise, pretty straightforward using AtomW. This is already, it's like 11 million characters, so 2 epochs is all I could afford for about an hour of processing on my laptop. There's some freedom in terms of the batch size and learning rate. I just chose those parameters. They seem to work pretty well. And the result was I was getting 55% test accuracy. And if you remember, the MLP gave us 45% and the bigram gave us 27%. But even though it's maybe not a huge jump in terms of test accuracy, the generated result is actually much better. So what you see the overall structure where there's the actor, colon, new line. In this case, it's giving all capitals because a lot of the data set is capitals for the actors' names. And then you have actual words. Sometimes they're kind of strange words. I don't know if this is a Shakespeare word or if this is a made-up word. But, most of them are actually words. A few of them are, maybe the capitalization is capitalized, or the pluralization is capitalized, and so on. But overall, it's way better than what we were getting before. It's kind of funny to read it, but it sounds pretty Shakespeare-ish. So if you want to do more, if you have more processing power, so this guy Andrei Karpathy, he has a really nice sequence of videos that basically goes through the bigram and builds you up to this style of model. Although he codes it much more bare bones in PyTorch, he doesn't use like nn.linear or anything that he just uses matrix multiplies and stuff. But he configured the same architecture with longer context length, larger embeddings, a few more heads, a few more layers, and he trained for 15 minutes on what at the time was the most powerful NVIDIA GPU. Those cost at the time about $10,000 a piece because we bought a few for my research group. And they're about 100 times faster than a CPU, roughly speaking. And for 15 minutes, you can afford to, I think he actually did only a fraction of an epoch, not even a full epoch. But if you look at his output is definitely a little bit better. You don't see those really strange words as much. The words look pretty good. Well, okay, there's a few weird ones, but overall, I would say it's an improvement, which you get just by scaling. And that is kind of the cool thing about the transformer versus the older models like the RNNs. If you scale up an RNN, you just make it bigger, it just kind of saturates. But if you scale up the transformer, it just keeps getting better and better and better. Of course, to scale it up, you need to also scale up your data, scale up your processing power, but you just keep getting better and better results. And there's like a whole field of scaling laws for how people analyze these, and they can kind of predict like, okay, if we keep growing our compute and our data, we're going to keep getting better and better and better, and there's some theory to it. But he also has a slightly refined version of his code base called NanoGPT, which is really nice. And that handles both words or characters. And it can load OpenAI's GPT-2 model. And it can actually train that model. If you have enough resources, you can basically recreate GPT-2. We'll talk more about the different models next time. But it's only like 600 lines of code. So it's pretty straightforward. But you can do real stuff with it, actually. So that brings us kind of to the end of learning about the nuts and bolts of attention and transformers. And what we're going to do next is we will just talk a little bit more generally about large language models, like the history of them. This is what was in the first one, then this is what the first OpenAI one, and this is the improvements they made over the years, and how everything kept scaling bigger and bigger, how much it costs to train. And then we'll talk not only about the pre-training, which is what we focused on, but the fine-tuning, post-training stuff that you need to actually turn these into chatbots. And then eventually we'll talk about a really nice Scikit application. We've been using Scikit-learn, but there's something called Scikit LLM that allows you to interact with any of OpenAI's models, any state-of-the-art model, to do a lot of different machine learning tasks. It just makes it super easy. So we'll see some examples of those. But we'll continue this on Wednesday. See you guys then.